Clint Kelly. I work at WibiData. I'm going to go without the microphone. If you have any problems hearing me, just let me know. I can pick up the mic. It's no problem. Today I'm going to talk to you about Kiji. Patrick gave a nice introduction to Kiji in his kickoff for today. It's an open source platform for building real-time big data applications. And we've recently added support in Kiji for Cassandra as a backing data store. So first, a little bit of motivation. Let's say that you want to build a big data application. Put a couple of canonical examples up here on the slide. Maybe you're working at a retailer, for example, an online retailer, and you've collected a lot of data over the last several years about your customers, all of the goods that they've purchased, what they've clicked on, what they've looked at, and so on. And you want to enhance your site such that you take all of this data, you probably run it through Hadoop or Spark or something like that, do some machine learning on it, and train an algorithm, maybe calculate item-item similarity, something like that. And then you want to take these trained machine learning models and you want to use them in conjunction with some context for the way in which your user is interacting with your site right now. If you're building a retailer, for example, you might want to look at all of the items that someone has in his or her shopping cart, everything they've looked at in the last 10 minutes on your site, and use that to recommend some new stuff that they might want to buy in real time. So how do you go about building this? Well, right now there are a lot of pretty awesome open source technologies out there. Again, talked about some of these earlier, obviously Cassandra, which we're all here to learn about. And then other data storage layers like HBase. There's some great computational frameworks out there like Hadoop, also Spark, and then tons of stuff built on top of these different frameworks. Hive, for example, or Pig for querying data. New DSLs that are even more abstract on top of MapReduce, things like Scalding from Twitter, even stuff like Impala. There's all kinds of stuff out there, but to get from that to building one of these applications is pretty non-trivial. There's a lot of plumbing you need to use to connect all these different open source platforms together, and there's a lot of additional functionality that you need to build, and it's not simple. And so with that in mind, we developed, over the last several years, Kiji. And the idea behind Kiji is that it's a platform that can help you can use as a bridge to get from all these different open source technologies to your final big data application, whether it's online retail and recommendations, other kinds of analytics, and so on. And make yourself happy. So a little history of Kiji. It's developed at WibiData. We're a small startup in San Francisco, originally founded by some folks from Google and Cloudera who had worked on solving these kinds of problems in the past and want to produce a more general framework that would enable others to benefit from what they've been learning and the lessons that they've learned. One thing that's interesting is that we originally built Kiji exclusively on top of HBase. And I'm going to discuss the Kiji data model a little bit later, and there might be, a lot of it will be really familiar to anyone who's used Cassandra, but there are also a few things that might look a little funny, and those are mostly because it's built on top of HBase. And as Patrick mentioned, there's been a lot of customer interest in using Kiji from customers who are currently using Cassandra, and so this year we've worked on adding supporting Kiji for Cassandra. So again, one thing to keep in mind that I think is interesting in this talk is that rather than building an application from scratch that would run on Cassandra, or taking an application that we originally built for HBase and then later porting it to work on Cassandra, instead we're building a single framework originally for HBase that now provides a single data model and a single API on top of two different NoSQL databases. A quick overview of the talk. I'm going to begin by describing in about 3 slides the Kiji project, all the different components of Kiji, and how these make it easier for you to build one of these big data applications. Then I'll go over the Kiji data model, some of the high points of it, and Then talk about how we map the Kiji data model onto Cassandra, what some of the challenges are, the current status of the project, next steps, and how you can try it. So first, the Kiji project. Usually think of the components of Kiji as falling into three main categories. First, there are some components that we use for real-time scoring. I had trouble figuring out how to visualize real-time scoring. I don't know, this is the best I could figure. So there are things for doing real-time scoring, some batch machine learning, other things offline, and then the data storage layer, which interacts with HBase and with Cassandra. The real-time components, again, are used for doing scoring on your website, taking some website or whatever your application is, taking some data that's changing really, really quickly. Again, like what people have clicked on in the last 5 minutes, what's in a user's shopping cart, and so on, and applying that to a trained machine learning model and using that to give some feedback to your application. We have a lot of sophisticated systems for managing different trained machine learning models. A lot of the time in an application like this, you'll have multiple different models that you're working on at once. You want to run some A/B testing or different kinds of experiments. So we have a pretty good system for uploading models to your website, deploying them, taking them in and out of production, and so on. There's also a REST server that you can use, that your application can use to interact with Kiji. On the batch side, we have a nice, really expressive design-specific language that you can use to describe MapReduce computations. It's based on Twitter from Scalding, which is really nice. It's similar to the API you'd get from Spark or Hummingbird. If anyone's used those, it's Scala-based. It looks like you're interacting with the collections library in Scala. We also have a machine learning library full of whatever you need for building your big data application, item-item collaborative filtering, things like that. And then hooks for talking to all of your favorite tools that your data scientists might want to use, things like Hive, and soon adding support for R also. Then finally, there's the data layer. We call this Kiji Schema, and this is what I'm going to talk about most today. So this provides Kiji Schema. It's funny, when I started working on adding support to Kiji for Cassandra, we found that especially in CQL, Cassandra had a lot of the things that we'd added to Kiji Schema to make HBase easier to use. So I've left all of that out of this talk, but a couple of other neat things we add. We have one is we use Avro for complex records. This is similar to the user-defined types that Patrick talked about this morning. So you can have complex records with named fields, nested lists and maps, and so on. And we also provide, again, a reasonably sophisticated system for managing different schemas. So if you're building one of these applications over time, you might want to add some fields to your records, take away some fields. The date you might change something that was a float to a double or wasn't int to a long or something like that. So Kiji Schema provides a mechanism for letting your schema evolve, registering different readers and writers, and making sure that everything's going to be able to read from and write to the database without any issues. And again, something to keep in mind is that it was originally built for HBase, and now we've added support to this for Cassandra. And again, as Patrick alluded to earlier, we're in production now, which is pretty exciting. There's one Fortune 500 retailer that's serving live recommendations online with Kiji. And also Opower, who recently went public, uses Kiji for logging energy data. That's a great example of the time series data that Patrick talked about, and uses it for doing some analysis and generating reports. So that covers a quick overview of Kiji. And now I'll get into the data model. The data model is pretty straightforward, as you'd expect. All the data exists in a collection of tables. Those tables are composed of rows, and every row has a row key and some data. In Kiji, we call the row key an entity ID, and the entity ID, we support composite entity IDs. So you can have multiple fields from your data model that you use to index a row, and some of these are hashed, some of them are unhashed. again, as Patrick was explaining before, like the hash components you can use to make sure that you distribute data evenly among all the nodes in your Cassandra cluster, the regions in your HBase installation. And the unhashed components you can use to enforce some kind of ordering in the rows in your database in case you need to do some scans over a certain range of data. So here, let's say that we're building some kind of example application. Let's take an example. Let's say we're building something similar to like Spotify or RDO or Pandora, or building a music application. This is one of the kind of canonical NoSQL data modeling motivators you'll see as you read more and more documentation and go to more talks and so on. So the data within our row we organize into column families. Again, very similar to what we do in Cassandra and in HBase. And so let's say for our music application, we have some structured data for every user. This would be things like the user's email address, maybe his payment information, mailing address, maybe a little avatar for the website and so on. And then we have some time series data, perhaps all the songs that the user has listened to since he started using our application. Within every column family, we have naturally distinct columns. We refer to the column names within the column families as qualifiers. So in this case, here we've got the email and the payment information for our user Bob. And let's say that Bob is on kind of a Beatles binge right now. He's been listening to a lot of Beatles music. So we've chosen, in this data model, we've chosen to name every column with the song, name every column with the name of the song that Bob has listened to. So here where our data model differs a little bit from what you get in Cassandra and where you can kind of see the roots in HBase is that every column can also have multiple time-stamped versions. So whereas Cassandra, this is something that you can add to your data model as Patrick demonstrated a few minutes ago. In Kiji, we have built-in support for this kind of time series data. And then within every version of a column, again, you can have a complex record. We use Avro for this. So that kind of covers really quickly the logical organization of data in Kiji. Again, you have rows that have column families. Within every column family, you have columns. Columns can have different time-stamped versions, and we use Avro to assign complex data types to the different columns. So now let's look at how data is organized physically. And one of the goals in developing Kiji and Kiji Schema was allow you to kind of think of the logical organization and the physical organization of your data separately. So let's take and this is similar again to what Patrick just spoke about, where you want to arrange your data physically such that it maps really well to the different kind of queries you're going to do. In an application like this, we might have a couple different query patterns. Let's say that we have some data where maybe all the songs you've listened to in the last hour or in the last day, and those might be the ones that we want to look at for serving recommendations in real time. Maybe we want to look at all the songs everybody's listened to in the last day, and that might indicate what kind of mood you're in, and we want to serve recommendations. We want to recommend to you songs that are similar to the ones you've been listening to right now. And then on the other hand, we might also want to keep track of all of the music you've listened to for the last year, the last 2 years, and then use that for some batch machine learning jobs that we might run every day or so with Hadoop. So just take the data model I just demonstrated and maybe divide it up into a couple other column families, one for songs you've listened to in the last day and one for last year. And then we still have the structured information. So the structured information, probably we only need one version of this column. Access speed might not be a big issue. The songs we've listened to today, if we're using these for real-time scoring, this kind of data we want access to really quickly, you might want to cache it. And it also expires really quickly. So we'll probably set a TTL of 24 hours for all of this data. And then the data for machine learning, access not such an issue, but we're going to keep it forever. So in Kiji, we have a notion of, oops, oh, I screwed up my graphics. Sorry about that. We have a notion of locality groups. So you can group one or more column families into a locality group. And these locality groups have common properties like the time to live for the data, whether the data is cached or not, whether you're using compression. A lot of these options are similar to what you'd get in a table in CQL. So in our case here, we might separate these three different, you can put more than one column family into a locality group. In this example, I've just chosen a one-to-one mapping. But we could put these three column families into different locality groups and then set some options for whether we want it to be compressed, cached, and so on. And one thing that's important to note here is that even though we've put these column families into locality groups, everywhere in your application logic, when you reference data, you only use the name of the column family and the qualifier. You never reference the locality group. So if you want to move columns between locality groups, for example, that doesn't change any of the other code in your application. So quick overview of Kiji Schema. Again, it's similar to what you'd get in Cassandra and HBase, and naturally, therefore, also Bigtable. It was originally based on the data model for HBase, so that's why we get this explicit support for different timestamp versions of the same column. We tried to separate the logical and the physical organization of data. And I also have support for complex data types and evolvable schemas. OK, so now I'm going to talk about how we take this data model from Kiji and map it to Cassandra. The first place we'll start is with the locality groups. As I mentioned, these kind of control how you're organizing data on disk. If you have data for one particular query, or one query pattern, you probably want to have it all co-located on disk. So we chose to map these locality groups to tables. And as I go through how we map the Kiji data model, the Cassandra, here on the bottom, I have the CQL for building a Cassandra version of a Kiji table, just to kind of illustrate what I'm talking about a little bit more. So for every locality group, we're going to build a separate table. Then the entity IDs map to the primary key in Cassandra. Within Cassandra, if you have within your primary key, you can have kind of two types of columns. You have partitioning columns, which go through your murmur3 or MD5 hash and determine what replica node hosts that data. And then there are also clustering columns, which don't get hashed and which you can use to control the ordering of data within a wide row. So the hashed components of our entity ID, we map to the partitioning columns in Cassandra, and the unhashed components we map to clustering columns. Next, the column family, the column qualifier, and the timestamp. All these other components that you use to identify one unique instance of a cell in Kiji. We also map to clustering columns. And one thing to point out here, we're sorting all the data, again, as Patrick demonstrated in his talk. And again, we're sorting by, everything's in ascending order except for the timestamp, or version, as we call it, which is sorting in descending order. So again, if you want to get the most recent version of a cell, you can just use limit 1, and it's available right away. And the column values, because we're using Avro to serialize these complex records, these just map to blobs. And here, just to kind of give you a flavor for how this works, if you have this data in a Cassandra table, you can query it in CQL. And you see that you get one unique row in CQL for each unique data value in Kiji, which is what you'd expect. Fortunately, the values of the cells are kind of a garbled mess because they're all serialized. We have some ideas on how to alleviate that pain. And again, just to recap, this shows how the data in one of these Kiji tables implemented in Cassandra would be organized on disk. So again, it's sorted first by the partitioning columns in your Cassandra table, and then by all those different clustering columns. So the parts of the entity ID that are unhashed, then the column family, the column qualifier, and the timestamp. Again, as Patrick said, if you want to have efficient queries, you want to make sure that you've designed this data model such that you're doing continuous scans and not jumping around everywhere. So let's look at how you now map a query in Kiji to a query in this Cassandra table. And one thing I should note here is that Kiji is a lot more permissive in the kind of queries that you can do than Cassandra is. Even though so when we're designing a Kiji table, we want to put everything that we need for a single query in one locality group. But we still allow people to do queries that cross locality groups. In the HBase implementation of Kiji, in fact, you can do all kinds of different compare and set operations and so on that cross different locality groups. So this can get a little hairy. So let's look at again our example of our little music application here, and let's say that we just want to look at all the information in Bob's info column family. Maybe he's editing his account information, something like that. Want to serve that on a website, or excuse me, on a web page. And this is a pretty straightforward query. We're just getting the data from a single column family. So we just have to specify all of the elements for the partition key, for the partition columns and the clustering columns up until we get to the qualifier inversion, and we'll get all the right data back. Actually, there is a bug in this slide. You don't need the limit 1 here, because in the definition I showed earlier for the locality group, we set the max versions to 1 anyway. So we'd only store the most recent version here. But anyway, this is a pretty straightforward translation of this query. No problem, 1-to-1 between Kiji and Cassandra. Now, where this gets interesting is if you have to support a query that crosses crosses locality groups, and therefore crosses your CQL tables. So let's say that maybe Bob's emailing his buddies with some information about the last time he listened to one of these songs, or he's posting it on Twitter or something like that. And we need to get some information from the info column family, as well as some of the structured data from the last time, or some of the complex data from the last time he listened to the song Help. So here this gets a little tricky, but it's pretty straightforward to implement. We just have to do 2 separate queries, one to each of the Cassandra tables that represents a locality group in Kiji. So this, there's no problem, works pretty well. And again, one thing that's kind of neat, because we're fetching just the most recent time that Bob listened to Help, and because of the way we order all of our queries, we just use limit 1 and get the most recent value back. So now let's say we want to do a query that's more like what we might want for some kind of batch machine learning process. We want to get all of the information, or all of the songs that Bob has listened to for a given period of time. So instead of getting, looking at just one song, like getting the most recent version of the time you listen to Help, now we want to look at all of the listen events for him in a given date range. So this looks like a pretty straightforward translation again to Cassandra. It's similar to what we did on the previous slide, but here instead of having the limit 1, we just specify a timestamp range. Unfortunately, this doesn't work in CQL. There are some restrictions that are there to prevent you from doing kind of asinine queries like this. If you look back to how the data is organized on disk, if you do a query like this, you're going to be skipping through tons and tons of data. Cassandra is really going to have to go through all of the data you have here for this entire songs column family, and then just skip everything that's outside of this time range, and it's potentially really expensive. And one thing I'd also mention, since we've been talking about data modeling, this would be a horrible data model if you ever want to do a query like this. But in Kiji, it's something that we allow users to do, even if it doesn't work out so great. And you can do things like this in HBase also. But this blows up in Cassandra, so we have to work around this in Kiji. And a lot of the work in providing support for Cassandra in Kiji has been identifying corner cases like this and figuring out workarounds. So what do we do about these kinds of tricky queries? I showed earlier that, well, a lot of time you can just filter in CQL. You can use inequalities on some of the different clustering columns, and that works most of the time. And it's usually a sign of a well-designed, usually if you've designed your schema appropriately for the access patterns for your database, this will be sufficient. Sometimes for queries that cross locality groups, even sometimes for those that don't, we can break up one of these Kiji queries into multiple CQL queries. The fallback plan, which is pretty ugly but does work as long as you have enough memory on your machine, is just to fetch all the data you could possibly need and then do filtering on the client. So as an example, in this query, we could just fetch all of the music listening history for Bob over the whole time he's used our application, which hopefully is a significant amount of data if our business is successful, and then just filter it on the client. But that's pretty terrible. And the bottom line is that designing a table layout is pretty important. So really we have to work with the Kiji users and educate them about the best way to design schemas such that they match their query patterns well. One other thing I want to mention is that we used, in the implementation of Kiji Schema, we used the Java driver and the native protocol exclusively, and this Java driver has a really nice async API that lets you use futures and blast out a lot of queries in parallel before you get any data back. And so that helps a lot with the performance of breaking these Kiji queries up into multiple Cassandra queries. One other thing, just wanted to note while we're discussing how we ported Kiji to work with Cassandra, we had to rewrite some new input and output format classes for Hadoop. Again, this is mainly because one Kiji query that you might want to use in a MapReduce job can generate multiple Cassandra queries. So we have a new MapReduce format. It also works with Hadoop too. And again, we use the Java driver instead of the Thrift API. And using these input and output formats, you can combine the data from multiple Cassandra queries into one data structure that you get in your mappers. So the status of the project, we have an initial release coming in 2 weeks. This is, I guess, somewhat of an alpha release. I went through a lot of the different components of Kiji earlier, and this initial release will include support for Kiji Schema and for running MapReduce jobs, but it's not yet been fully tested with the rest of the entire Kiji ecosystem. Over the next quarter, we're going to work first on adding support for Cassandra and all of the other components of Kiji, all the batch stuff, real-time, and so on. And also work on exposing some of the kind of neat things you can do in Cassandra to Kiji users. I've already done this in HBase, so we want to kind of choose to do the same thing in Cassandra so that you could use the programmable consistency levels, for example, maybe sometimes you want to do you want to use 1 for the consistency level for your writes, maybe sometimes quorum and so on. And finally, we've looked at better ways to integrate Kiji with Cassandra such that if you're using a non-Kiji tool to look at data in a Cassandra database, it looks natural. And right now, the biggest place where we fall short with that is the value of the data in your tables, since those are all stored as blobs. We have a command line interface for Kiji that deserializes these blobs and renders them as text when you're looking at it, but it would be pretty straightforward to maybe fork the CQL shell and do that deserialization there so that you could inspect the data in your tables that way. We've also looked at just when we read and write to and from Kiji tables, taking our Avro data and actually mapping it to the user-defined types that are coming out in Cassandra 2.1. So one thing I wanted to mention is that thanks to everybody in the Cassandra community, we only got started on this project a couple of months ago, and everyone on the user list has been really helpful. There are a lot of awesome videos out there. Most of the webinars, the meetups, and so on or the Cassandra Summit are all online. That was a big help. And the free training from DataStax and so on made it really easy to get up to speed. So finally, if you don't want to wait 2 weeks, you can go to kiji.org and download our development kit. This is a tarball. You really just have to untar it and run one command, and you'll be up and running with a full Hadoop and HBase cluster. In about 2 weeks, we're going to add support. That will also include Cassandra. And there are a lot of tutorials online for learning to work with all of the different components and learning how to build a big data application with Kiji. And also, if you're interested in working on this, we are hiring also. Okay. Oh, perfect. So, anybody have any questions? Yeah.
So this queries that we do.
Yeah.
And the Kiji is running on top of Hadoop. So this queries Kiji actually doesn't run on a job.
No. So the queries I was showing before, those map directly to HBase or Cassandra. We have a separate part of the ecosystem that you can use for running MapReduce. And if you're going to use Hive, though, then that would be
The Java driver that you mentioned, is it a Java driver WibiData or?
Oh no, sorry, that's the DataStax Java driver. It's kind of an evolution of, or I guess kind of a replacement for the Rift API. Yeah, go ahead.
You are majorly working probably on the Hadoop infrastructure, right? So why do you choose Cassandra over Hadoop? What was the decision making?
Oh, well, Cassandra is really a complement to Hadoop, and we were originally working with HBase, and there was this customer demand for Cassandra. A lot of people in the space we're going after at WibiData are using Cassandra and asked us to add support for it. Anybody else? Yeah, sure.
For someone who is already using HBase as a backend for Kiji,
yeah.
How difficult is it to migrate?
So it should be pretty easy to migrate. You could just write a MapReduce job to dump out all the data in your HBase Kiji table, and then use a bulk importer to load it back into the Cassandra one. And you should be able to use all the same Kiji files that describe the layout of your table and all the same code to access it. Should work without any modification.
Do you have to modify the arrow schema that you have?
You shouldn't have to modify anything. So the exact same layout file will work with both. Oh, yeah, go ahead. So we haven't done performance testing yet. That's something that's on the agenda for the next few months. But I'd expect that we'd see whatever the normal trade-offs are between HBase and Cassandra.
Was there any feature that you lost, any feature that you gained when you HBase?
So one of the big differences is that HBase has support for a lot of really rich server-side filters. So you can do filters in HBase that let you filter the data coming back by like a regular expression on the column qualifier or the column family, even the value, and all kinds of different version filters and so on. So that was one of the, as I showed earlier, we can kind of replace that with inequalities in the CQL query. But that's one of the big features that is kind of missing right now, and we're looking at options for implementing that in Cassandra. There are a couple other projects out there that do support doing some additional operation on the server. Yeah?
So I noticed you have column family.
Yes.
And DataStax is kind of not encouraging people to use column families. So what's
So the column families here are in the Kiji data model. So within Cassandra, those the names of those column families just map to a single clustering column within Cassandra.
So you don't have column families?
No, so I'm not totally sure what you mean by column families. I know previously in Cassandra, what was called a column family is now called a table in CQL. So and we are using those. And then there used to be super column families and things like that. But we started supporting this in 2.0.6. So
So you're not using threads, you're just using...
that's correct.
Okay.
Do I have time for any more? Okay. All right. Thanks, everybody.